This meeting is being recorded.
Okay, welcome everyone to this webinar sponsored by the Chicago DOE Alliance Center and focused broadly on chemistry, physics, and materials at extreme environments. This will be our 68th webinar, some jointly sponsored by our partner in an essay laboratory, CDAC, UCSD. And today we're pleased to kick off the new season with Tim Jenkins from Army Research Lab, who's graciously agreed to give this talk. Tim is a research scientist at ARL and studies materials in various extreme environments with a focus on energetic materials. He has a bachelor's from Lafayette College and a PhD from Syracuse, which he received in 2004. He was a postdoc in our group when we were in Washington from 2004 to 2007, before moving to NIST, where he was a scientist at the NIST Center for Neutron Research. In 2012, Tim moved to another part of Maryland, to ARL Aberdeen, where he's been ever since. He remains a close collaborator on materials such as energetic materials in extreme environments through an ARO-funded center we have. And he's also a frequent user of synchrotron facilities such as APS. So Tim, we're delighted you're kicking off our series this year, and we're looking forward to your talk.
Great, thank you very much, Russ. And I want to thank CDAC also for the opportunity to talk a little bit about our research. As Russ said, I've been working at the Army Research Laboratory for about 13 years now, 12, 13 years now. And while I love working here, my favorite time was always when I was working with in the geophysical lab. That was a really good experience, and I appreciate. I want to thank Russ for the opportunity early on in my career. So a lot of this work was done in collaboration with Dr. John Benyon, also at the Army Research Laboratory, and he's on this call. And hopefully, if I say something too drastic, he'll jump in and correct me. But moving to a little bit about the Army Research Laboratory for some people that may not be aware. We're a fairly large research laboratory funded by the Army to do a lot of the foundational fundamental research that lies a little bit outside of the mainstream areas for a lot of these research focuses, and particularly focuses on operationalizing this science for overmatch in our future conflicts as a country. So the way I interpret this is that Army does a lot of fundamental research, much like a university, but we have an eye towards a focus on a specific application, say how this can be used to benefit our customer, which in our case is the U.S. warfighter. So along the bottom there, you'll see a lot of our core competencies. They range from biotechnical sciences on the left. You have energy science, cyber science, quantum, and then the three at the very right there, science of extreme materials, terminal effects, and weapons sciences are the ones that I'm more familiar with and involve myself more with. And I work underneath the weapons sciences directorate. So this is going to focus a little bit more on explosives and energetics for this topic. And eventually we'll get to talking about stereochemistry and how pressure fits into this. But I want to try to give a broad overview. If you see anything in this that fits into your research, please get in touch with us, because we do love to hear new ideas that might be relevant to what our mission is. And we're always looking for new collaborations to benefit our mission. So hopefully these videos are playing, but across energetic materials is a very broad topic, covers a lot of things. I know a lot of people on this talk are very aware of this, so I'm not going to belabor this too much, other than to say, just to remind you a little bit about what we're trying, what the differences are between explosive and propellants. Pyrotechnics ends up being a little bit of an outlier. We're mostly focused on explosive and propellants. generally, there's a lot of different tailored uses for these things. Explosives have a definite pressure component to them, and they need to withstand a lot of forces and extreme environments, much pressure being one of those components. And then propellants are used a lot in generating the thrust to propel your charge or your warhead or something like that. And there's usually a lot of pressure, gas pressure involved in that. So both of these two areas rely a lot on understanding how these materials respond under extreme conditions. So this is a really good area to leverage this tool of high pressure research. So moving to specific energetics, and in this case, we're talking explosives. There's a timeline here. You can see essentially when certain energetics show up, going all the way back to the 1863 TNT discovery, then all the way back up to 1980s, which now is used to be, I thought it was like 20 years ago, but now it's easily 40 years ago. So when the CO20 was discovered. So these represent our core toolbox of energetics from TNT, RDX, and HMX and CO20 as primarily used in certain weapon systems. And you also have TATB in the lower left there. And that has a sort of a unique application. We'll talk a little bit about that in a second. Underneath the molecular pictures, you can see the density, the detonation velocity, and a measurement of sensitivity. In this case, it's impact sensitivity. So you can notice as you go up in performance and get closer to the modern day, you see that the density of these materials increases. And this also corresponds to an increase in a detonation velocity, which is our general measurement of performance. But we also notice a decrease in sensitivity, meaning that these are more likely to be triggered by impacts, or like they're more likely to be set off easier. So this means that they are a little bit more difficult to handle. The exception to this is TATB. This has a very high impact sensitivity. And there's a specific application for this where you want to have an energetic that doesn't have the ability to be set off without a very specific amount of energy put into it. So like if you were to drop this thing, it would not go off. And I'm not going to talk too much about that, but just to point out there that there is a general correlation between both the detonation velocity, density, and sensitivity. So of the key components, the density, of course, is tied to the power, like I said. And additionally, we care about safety quite extensively. This is tied to both the sensitivity in the case of the impact here, but also the stability over a long term. So ideally, we want something where the material maintains a lot of these properties over not just days or weeks, but like months and years. And this is due to the fact that as we put these into a weapon system, we want to know that if we stick it on a shelf or in essentially an explosive bunker, when we take that out in a couple of years, we'll be able to see identical performance, and we don't have to worry about any potential issues. And this comes up in I'll talk a little bit more about this in a little bit later slide. Lastly, and this isn't really captured in this timeline chart, we want to have a processability, and this is important for handling the energetics, both from the synthesis aspect of it and also how we handle the energetics in a weapon system application. So this is synthesis and also a thermal property associated with the materials. And in the case of this research that I'm going to talk about today, the melt point becomes a very key component. So that's a little bit of our space that we're playing in from the energetics aspect. While we're talking about this, I also want to touch upon crystal polymorphism and how this applies to the energetic materials. So everybody on this talk is quite familiar with different phases of materials, and that if you increase the pressure and change the conditions, the material can go to different phases, which have vastly different properties. A lot of this is one of the tools that we use in my research to try to find new energetic materials for use in the Army's applications. But another way to think about this is some cases we don't want to find a polymorph. We want to have a material that is very stable over a large pressure temperature range. So in the case of Cl20, which is shown in the lower right, that material is the epsilon phase has the highest density and therefore the highest detonation velocity. So it's packing the most power. And ideally, that's the form of the material that you want to use in your weapon system application. But there's several other thermodynamically stable phases that can show up at decreasing density. So where you get to the lowest density, excuse me, you have a performance much like you would have with an HMX molecule. So that's not as favorable for a weapon system application. Additionally to this, a lot of times it's tough to predict how the material, the different polymorph of the material will respond under a shock or friction application. So it adds a bit of uncertainty into the weapon system and how you would use and handle this material. And when you're talking about energetics and explosives, you really don't want to take a lot of chances. So we really want to understand these things from front to back and from top to bottom. So this is an example where we can use high pressure to understand how this material responds under these pressure conditions. Because the diamond anvil cell technique is such a small amount of material, it involves a very low amount of risk to the experimenter and to any kind of measurement that we would take. And because it also uses a very small amount of material, we can do this very early on in the characterization phase of energetics, which is something that we have to do on all materials that we make in order to move them up to different scales, primarily for understanding the safety response and also to identify potential issues before they become catastrophic. So a lot of the data that we determine using the diamond anvil cell goes into an early evaluation phase of these structures. So excuse me, taking a step from the different phases of energetics, I want to talk a little bit about how we process and handle these materials on a bulk scale, because that essentially ends up being the scale that a lot of these things are handled on. It's kilograms, it's large quantities. So one of the ways of dealing with these is at a melt cast application. And it turns out TNT, which is coming up on its 160th birthday, is still essentially the state-of-the-art melt cast energetic. And this is primarily due to the economics associated with making melt cast materials or melt cast energetics. It's very cheap to make TNT. Unfortunately, it is also an incredibly toxic process. And a lot of the sites that were used to make TNT in, say, World War II, where we were doing, thousands of tons of this a year, are now Superfund sites, and they have a lot of issues with the toxicity in the ground. And in fact, even using TNT as in a weapon system involves that it does do some damage ecologically, not just from the explosion aspect, but from the distribution of these toxic chemicals when it's used. So a lot of the testing sites where we do a lot of the material testing, they also have ecological concerns associated with them. So there's a lot of thought and research going into trying to find a better alternative, much from the ecological standpoint, something that isn't as toxic, but also something that has enhanced performance over what TNT is currently has. So in order to be a melt cast energetic, you have to hit a couple key takeaway points. And one of them is that you have to have a melt temperature. And it's very desired to have this between 70 and 120 degrees C. This is because a lot of the processing that we want to do for safety aspects is we want to do it in a steam heated kettle. So 100 degrees C melt temperature is ideal for that. So there's this range here gives us a little bit of room to play with. Additionally to that, we want a nice separation between the melt temperature and the decomposition temperature. This is primarily due so that when we heat this material, we don't run into a state where we introduce a decomposition of it, or potentially a cook-off event. Once you make this material and you melt it, you want to pour this into a charge or a warhead. This material needs to cool, and upon cooling, for purposes of performance, you don't want to see a lot of shrinkage and therefore cracking that occurs. And this is one of the issues that TNT has, is that it has a little bit of cracking issues associated once it's cooled. So understanding that, there's additional material properties associated with this one technique of melt cast, which need to be considered that aren't necessarily apparent from the from just either the calculation aspect or the first look at it. So understanding that TNT is our component, let's talk a little bit about some specific formulations of melt cast that are used and fielded. So the one that pretty much everybody has heard of is Comp B. This is a formulation of RDX and TNT in a 60-40 ratio. We add in a little bit of paraffin wax to this. The paraffin wax acts as a desensitizer to try to increase the stability of the material, decrease the sensitivity to shock. World War II, this was used extensively, but it is still used today. And you can see an example of this in these 155 millimeter projectiles on the far right. These are projectiles that are filled with energetic and then capped with a detonator on the tip. And these are launched out of a artillery cannon. And if you've been watching the news, you see that this has been used even extensively today, even though it's a very old, artillery is a very old technology. When you're talking about Comp B, you need to be, there needs to be a careful of this. It has a couple issues associated with it. One of them is cook-off. And cook-off is the event where you heat up the material, usually to a temperature where you induce a energetic reaction that leads to a detonation of the energetic. And this was quite tragically seen in the USS Forrestal fire in 1967. So what happened in this scenario was a couple of bombs were loaded onto the USS Forrestal during the Vietnam War that were manufactured in the Korean War. So they had been sitting around for a long time. They had been exposed to extreme environments, and the material in the Comp B had started to decompose, and a lot of the paraffin wax used as a desensitizer had leached out of the weapons. There was a fire involving jet fuel, which involved these bombs, and then led to a detonation due to cook-off, which killed over 100 sailors and injured about 150 more. So it was a very terrible loss of a tragedy that resulted in a lot of changes to different policies involving energetics. So one of the things that came out of this was that all of our weapon systems sort of have a finite lifetime associated with them. So if you don't end up using these in a application, like you either drop them or you fire them off, they have to be decommissioned at a certain point. So it's a constant state of replenishment, which is why stability over time is a very, very important issue. Moving on from Comp B, we get to Octol. Octol is a very similar material to comp B, but instead of RDX, we now use HMX, which is a higher performing energetic and a higher concentration with TNT. This is currently used in a lot of our warheads. Just another example of a melt cast. Then finally, pentolite, which is a civilian strength energetic. We use another energetic, PETN, and a very high TNT formulation. And this is used primarily in blasting charges, mining, and it's very, very stable material. You can see to the right of that an example of what happens in a melt pour. You're physically melting it so it looks like a wax, and then you pour it much like you would a making a candle or something like that. So contrast that to a composition C or a C4, which is a plastic explosive. These have large amounts of RDX, but you also have binders and plasticizers. Where the melt cast has a very high or very rigid structure once it casts up, the C4 is very malleable and could be handled like putty. So there's going to be different applications for these different materials. So a C4 primarily used in demolition and various applications, whereas you would not put the C4 in a warhead due to its poor material properties. So I'm trying to highlight a lot of the reasons why we need to consider not just the density in the materials moving forward, because that comes important in this next slide here, where we start to talk about alternatives to melt cast materials. So traditional design of melt cast replacements for replacements of TNT has involved looking at purely the density and purely the melt temperature issues. So this is perhaps a little bit short-sighted, but in terms of the calculation, this is the primary thing that drives performance, is the density. So one of our synthesis group had the idea to try to look and borrow a page from the pharmacological community and see, knowing that different stereoisomers and regioisomers will have different material properties, see if we can apply that to the energetics. And in fact, you can, and this is what their paper talks about. Looking at these different materials, you can see that basically you don't see any, it's the same structure, same groups, same atoms, and the different arrangement. So what you see when you do the calculation is you see essentially the same energy output. But you do see vastly different material properties. This one's a little bit counterintuitive to traditional energetic material design, but potentially has a good application in this area. So they made a whole suite of materials, and looking down from them, you can start to do characterization of these individual structures. And I've taken the chart from the previous slide and blown it up a little bit so you can see all the numbers. Looking at the left, you see the numbers for TNT, and then TMETN, which is a liquid propellant. This is on there because there's one phase of this, one stereoisomer of this, it ends up being a liquid at room temperature. So this is maybe a case where a material that has a explosive property might also be used as a propellant, given the right conditions. So looking at TNT, you can go down and see there's a melt temperature at 80 degrees, and the decomposition is about 300 degrees. And then working down, you get to a pressure, which is a detonation pressure of 19.3 and a detonation velocity of 6950. So these are not really favorable numbers. You'd want to have something higher than that. In fact, some of the materials produced in this study have higher numbers than that. And you can see I've highlighted two of them, compound 2, which is the cis-trans-cis structure, and compound 5, which is the all-cis structure. So these are very, very similar to each other. In fact, you can look down, and the only small difference that you see is a slight difference in the density between the two due to the way that they pack in the crystal. This is then contributes to the difference in slight difference in detonation velocity that you see. Compound 6 also has a lot of interest as a potential melt cast energetic, but this is a regioisomer to these materials, and we wanted to try to look at the differences we could determine from a stereoisomer standpoint. We undertook a polymorph study looking at these materials, both 2 and 5, this cis-trans cis and the all cis form, just to try to see if there was a difference in, if we saw a change in the polymorphs or a change in phase, and then also trying to tease out some more information potentially about the material properties moving forward. So here's some work that we did using Raman spectroscopy on this page. You can, first of all, you can see the cis-trans cis and the all cis structures on the right there. And then looking down the different axes, you can see they have very similar packing arrangements. And in fact, their packing densities are very close. Their bonding interactions are very close. They have a little bit of the hydrogen bonding aspect going on, which helps to stabilize these structures. And in fact, if you look at the change in pressure with Raman, you can see pretty much that we don't have any new features that show up. We don't have any large phase changes or even very small phase changes. We do see a lot of peak broadenings under pressure, as you would expect from going up to relatively high pressures. These materials are not very hard materials, so they have an elastic response, but they do show a lot of peak broadening over over the course of the pressure range. Looking down, we can see the ambient pressure measurement and then also a decompression, and we don't notice any change from the ambient to the decompressed. So whatever structure or transitions that we don't see, we also then recover essentially the same material back. We don't see any essential damage in the structure. So because everything is sort of the same, we can then look at the compression over this pressure range with the X-ray diffraction, and you can see essentially basically the same sort of trends between these two materials with a couple slight differences. And I want to highlight those on this slide. First of all, you notice that there is a different bulk modulus between the two, and you can see that there is a slightly different volume change associated with the cis-trans cis and the all cis structures. In fact, the compressibility of the all cis is greater than the cis-trans cis. The other thing I want to point out here is that one of the techniques that you can use looking at the change in material macro structure over pressure is, of course, peak broadening. This has been used in various crystalline studies. I think it's one of these things where I haven't really used this a lot in my previous research, but this allows us to do a quantitative or qualitative comparison between the cis-trans cis and the all cis structure to try to figure out, given the great similarity between these two materials, what kind of material differences show up with increasing pressure. So looking at the cis-trans cis, you can notice that quite quickly when we increase pressure, we start to get a very large pressure broadening, and this becomes difficult to refine at very high pressures, in that above 20 GPa, it's tricky to fit these into a refinable volume change. So, but converse that with the all cis structure, which has a much less broadening of the peaks with increasing pressure, indicating that we're not developing the material failure on the macro scale that we are with the sort of the cis-trans cis arrangement. once again, we noticed that upon recovery and in comparison to the structure that was calculated from the synthesis paper, we noticed that we get everything back upon recovery. There's no decomposition, no issues with that. So looking at the volume compression from ambient to 25 GPa, we can see that roughly 32% to 38% volume compression. That's a 6% difference. That's not a gigantic difference in volume compression, but it is significant. And couple that with the material response to the pressure and the fact that we notice significantly more broadening of the cis-trans cis indicates that potentially this material might develop more micro cracks and stresses than the all cis. This allows us to potentially apply this understanding to how this material will respond under higher stress conditions. Mainly, we don't want to see in a high G gun launch environment something where we have cracking or delamination of the material under like a load or a shock load or something like that. All this is determined qualitatively, of course, early on in the research, and this allows us to down select which material to prioritize for further investigation if that's so warranted, and points to how diamond anvil cells allow us to leverage these techniques, this understanding at a very early stage of the research. So just to sort of summarize and wrap up, I hope that I've showed you a couple different ways of thinking about how energetic design can be expanded beyond just looking for the highest density. And when we look at energetic materials, we're kind of limited because of our applied nature of our research, where we want to have something that we can then use down the road in either in a practical application that benefits the soldier. We want to limit ourselves to the pressures that we look at. So very, very high pressures, while there's a lot of interesting science that goes on there, it's very difficult to use that in a practical application. So some of the ways that we can use high pressure research to understand the practical aspects a little bit better is by doing these additional processes and additional techniques. So this traditional energetics focus very much on density. We want to try to think a little bit more about that and understand that material properties as a whole can play a lot more of a role in how the material's utility ends up being used. So I've also hoped that you see that we can use the high pressure data to understand these materials a little bit better, and gotten across that diamond anvil cell experiments are a very low cost and high throughput tool for probing energetics safely and early on in the development process. I need to acknowledge a couple people here. Jesse Sabatini, Eric Johnson, and Ross Schwarza were some of the internal researchers that worked on the initial paper, the synthesis paper. They provided us with the material, which we used at the beamlines. We did this research at Sector 16, 13, and Martin's beamline at ALS. In addition to our internal researchers, they had a collaboration with Scripps research in the production and synthesis of these materials, and leveraging that cyclobutane geometry for energetic purposes. So I thank you very much for your attention, and I look forward to any questions that you may have.
Thanks very much, Tim. Great talk. A really interesting new area of work in energetics. Very fascinating. And thanks also for the overview of activities at ARL. So the talk is now open for comments and questions. Just put your question or comment in chat, raise your hand, or just unmute yourself.
Can I ask question?
Yes,
Sure.
go ahead, Fatima.
Yeah. Hello, everyone. Yeah, it was really nice presentation. Actually, it was real application of our field. Yeah, and I have some question. In the slide 10, you show that you have two different compounds, which one of them is orthorhombic, one of them is monokinetic. Yeah. And my question is, did you try to grow crystal at high pressure? I mean, you will choose, for example, 0.5 gigapascal, and you will try to do recrystallization at that pressure. Because I just saw you just compress it, yeah.
Yeah. So the way we do, so normally we would try, if we were doing a high pressure synthesis, we would try to make the crystal at high pressure. This is material that we got from an organic synthesis group, and it came essentially as received. They did a they produced the material on the gram scale, and of course the diamond anvil cell experiment needs very, very micrograms of that. So we usually take a couple single crystals that they have and use those as our material. So one of the things we do to confirm that we have the right structure is we do an initial crystal pattern, and we compare that to the published crystal that we get from that they took earlier in their research.
Yeah, but I mean, that is correct. But I believe if you try to recrystallize again the sample at the high pressure, is it possible you will find different polymorph or even different structure? Yeah, because I can see we have an orthorhombic PBCN, so I believe that space group can go even lower symmetry. So maybe you will find new polymorph or even new situation in trans or cis. Yeah.
Yeah. Okay. I see what you're saying now. Yeah. That's a very good point. Yeah. I think the what we were trying to do with this was just to try to see what differences can we see in the straight ambient to 25 gigapascal region. And to be honest, it's like there's a couple games that we can play at higher pressure, but we're really in this role, we're more of a characterization technique in that we can maybe make a new material, but we also want to understand the material as it's made and what the response would be under the higher pressure conditions. But I see your point, and I understand where you're going. The one thing that I love about this kind of research is the toolbox is so big, and there's a lot of things we can do to change the material, push the material into a new phase, make new bonding and new arrangements. It comes down to almost like a practical concern at this point, in that once we start thinking about practically applying this, it becomes, you run into the issues where you do too many techniques, then it's going to cost too much to make the material, the new material that you have. So it's a very good fundamental research problem, but it's maybe not a material that'll move its way down the road. But understanding how the material responds based on the stereochemistry is some knowledge that we can then use for other future research, hopefully. So
thank you.
Yeah.
Thanks very much.
Thank you.
So on this point, are you able to do single crystal diffraction? Do you have single crystal?
Oh God, I would love to do single crystal diffraction on this. It's just, yeah, those experiments, we're trying to do a lot of high throughput work on this stuff. So this is one compound out of several that comes out of this synthesis group. We want to make sure that we screen a lot of these. So yeah, if something looks interesting, we would definitely be more interested in the single crystal work. But those experiments are a little bit more involved for me than the traditional powder diffraction.
Yeah, okay, thanks. More comments, questions?
Russ, can I, sorry, Leonard here. Can I ask a question?
Yeah, go ahead.
Yeah, so looking, you know, TATB, for example, has a benzene ring. Some of these have benzene rings, some of them don't. Is there any correlation between its performance and having a benzene ring, or especially under shear sensitivity? Is there a correlation or not?
Yeah, there probably is, but a lot of this performance is due to the amount of nitro groups. So there is a stability associated with that, and I assume that that based on the packing and the interactions that you get intermolecular, it depends a lot on your crystal arrangement, especially for some of these RDX, HMX, traditional energetic materials. But yeah, like one of the reasons why this material is stable to very high pressure is the hydrogen bonding interactions that we see between the different arrangements. And this hydrogen bonding stabilizes and prevents a lot of these polymorphs from popping up potentially. But then also, there's in certain cases, the way that the materials pack, if you have like a sheet structures, or if you have like a herringbone pattern in your crystal lattice, this can all contribute to the stability and allows you planes of slip that might relieve some of the strain in the material before you get to the point where you've initiated or detonated it. So yeah, it's a really complicated problem, and because there's such a focus on energy and but also controlling the sensitivity, so it's not so touchy that it blows up basically on your lab bench, then yeah, there's a lot of things that you can do, but you know, that ends up being the synthesis problem that they have to address, is like, how do we account for that, those differences?
Yeah, thank you. And sorry, just quickly, one more is did you see any radiation damage from X-ray measurements on these, or they were fairly safe?
Yeah, so we don't usually see a lot of, I mean, oh, sure, I guess. Yeah, so we don't see a lot of radiation damage. In fact, we can recover the structure to ambient once we release the pressure. We've done decompression studies on these. They basically hold up pretty well, especially on certain beam lines, right, that aren't as hard as others. So yeah, I'm getting feedback from John. He's saying that we also rastered the beam to try to minimize that. So yeah, it's something we're aware of. We try to prevent that from showing up in the data.
Okay, thanks. Nice work.
Yeah, thanks. More questions, comments? Are there examples of this kind of difference in high pressure behavior for organics where there are stereoisomers that aren't energetics, or is this the first of its kind for any kind of high pressure difference? I mean, these are really remarkable differences at high pressure.
So we found a couple of instances where people have looked at differences in stereochemistry, but you're right, it's not a big bulk of research. It's maybe something that warrants a lot more investigation, maybe on the pharmaceutical side. But for the energetics, we do play in this high pressure regime, so it's something that I think if we decide to go that way in the future, it's something that we definitely have to be cognizant of, and we have to pay attention to. But it all offers up another knob or tool that we can use to do the practical application stuff. One of the problems that we generally run into is a lot of these stereochemistry reactions involve using quite expensive metal catalysts right now. So that becomes a cost prohibitive step, perhaps. Yeah, so we've seen some enantiomer research out there, but yeah, there's a lot more to do with this. I think this is just a first. They did this with the synthesis, and it was a novel thing for the energetic research, and I think it's also a novel thing for a lot of high pressure stuff too.
Right. Muhtar has a question.
Hi, Muhtar.
You want to ask it? He's asking about the pressure medium in the diffraction experiment.
Yeah. So we generally use helium. Yeah.
But then do you worry about helium getting into the structure?
For this stuff, I'm sorry?
Which can happen in organics.
Yeah. I guess we could redo this again with a different pressure media to try to discount that, but we're not. I don't anticipate that we'd see we might see a slight difference, but I don't think it would be drastic for this. But yeah, that is a good point. Thank you, Muhtar, for bringing that up. And Russ.
Sure. More questions? Okay, well, if not, thanks very much, Tim, for kicking off our series this semester, and thanks for a great talk. We look forward to interacting with you at ARL and at APS in Chicago.
Yep. Thank you again.
Okay. Thank you all for joining us.